AC circuit analysis, bridge circuit. Today we will talk about applications of bridge circuits for various situations. First, we will talk about how to measure impedance using bridge circuits. Then we will talk about how do we measure frequency using bridge circuits and similar applications. So, first topic, how do we measure impedance experimentally? Now let's go back to the definition of impedance. G is real part plus imaginary part. Now, we do not know either real part or imaginary part or both parts. Then we have to figure out how we find their values. So let me introduce you to the method we are going to use throughout the class. The figure on the left is a version of Wheatstone bridge. This Wheatstone bridge is very similar to the version you learned from DC circuit analysis. So let's look at this figure closely. It has impedances G1, G2, G3, G4 at each arm. It has a source. Now this time this is AC source, usually a sine wave. Then we have detector in the middle. This is a symbol for oscilloscope. Now, as usual, we have to find balance at the detector or the oscilloscope. That means when you see or watch the oscilloscope, you find zero current and zero phase difference between point A and B. Now, then what will happen to the circuit? In such a case, since there is no current in the middle, that means you have the same current I1 for both G1 and G3 impedances. In the same way, since there is no current at the center, you are going to have the same current I2 for G2 and G4 arms. How about the voltage drop? There is no current at the center. That means the potential at point A and potential at point B is the same. So G1 and G2 will see the same voltage drop. In the same way, G3 and G4 will see the same voltage drop. So when you convert these facts into equations, this is what you find. G1 I1, that's the voltage drop at this arm, is the same as G2 I2, that's the voltage drop at this arm. And voltage drop at this arm, G3 I1, will be the same as the voltage drop at this arm, which is G4 I2. So from these two equations, you are going to find the ratios between G1 to G3 or G2 to G4 or G1 to G2 or G3 to G4. And you find these two identity equations. So we are going to use these identity equations in the next slides. So first example, inductance bridge. We have known resistance values R1, R2. We have a variable resistor R3, and we have a variable inductor L3. Sorry, this is L3. However, the impedance of this arm is unknown. We know that it consists of coil, and also it may have some internal resistance, Ru. So we have to measure Lu and Ru. Now, at balance, that means we are going to use these two equations, either left one or right one. At balance, G1 to G2 is equal to G3 to G4. So, G1 is R1, G2 is R2, G3 is series of R3 and L3, which will become R3 plus J omega L3, and G4 is in the same way R unknown plus J omega L unknown. So let's solve this equation. In the complex equations, to make identity equation, both real parts should be the same and imaginary parts should be the same. So from these relations, we have these results. R1, R unknown is the same as R2, R3, and R1, L unknown is the same as R2, L3. Okay, so that's the theory. Then how do we measure or find it in experiments? Now, the real parts is easy. We use DC source power. Then we can ignore the imaginary part and only we think the real part of the equations. So from here we find R unknown. Then once R unknown is found, then we can find L or unknown inductance. For that we use AC source, or it's called AC excitation. Excitation means we are creating magnetic fields by electric current. So sometimes they use excitation instead of source. They have the same meaning. So when you use AC excitation and balance the circuit, then we can find the unknown inductance. Now, let me mention some more facts on this inductance bridge. When you look at the balance question again, this balance question is independent of frequency. So you can use any frequency to find balancing in the experiments. However, usually we choose a frequency where it makes the reactance of inductances similar to the resistance value, because that will give you easy calculation here. Okay, so let me go to the next example. Capacitance bridge. This case we have known capacitance and unknown capacitance in the bridge. And sometimes the capacitance can have internal resistance. Now, DC current cannot flow in this circuit. Once DC current flows, then it will fill the capacitance. Then these two arms will be cannot allow current flow anymore. So DC current cannot flow in the circuit. So that means balance should be reached with AC current. Then let's look at this circuit. In this circuit, I use the notation such that the R1 or R2 resistors are the variable resistors. This is one way to use the bridge. There are other ideas too. I'm not going into details here because it will be too boring for you. Okay, so let me just mention one idea before I go to the next slide. If a bridge circuit consists of variable resistors and variable inductors or capacitors, one can measure in resistance, capacitance, and inductance based on the same circuit. So somebody can construct a bridge which can measure all three unknown stuffs at the same time. Now, let's go to the second topic. How do we select a particular frequency experimentally? Frequency means either omega or f. So, let's use the beam bridge example. This bridge has two RC pairs. Now, at one arm, resistance and capacitance are connected in parallel. On the other side of the arm, resistance and capacitors are connected in series. So it has both parallel and series RCs. Now, then what happens to the impedance? For this arm, since it is connected in parallel, we have to use the inverse of the values. 1 over G3 is inverse of the reactance for the capacitor plus inverse of the R3 value. Then when we invert G3, we can get this kind of value. Right-hand side is series circuit. So the value can be easily obtained by adding resistance value with the reactance for the capacitor. Now from the balance equation shown in the several slides before, this is the balance relationship. We can find the relationship between R1, R2, and R3, C3, R4, C4. For G1, we use R1. For G2, we use R3. For G3, we use the equation found here, and which is this one. And for G4, we use the equation found here, which is this one. So let's look at this equation. We are continuing next page. So from this equation, when we put the denominator part to the other side of the equations, this is what we find. Now this has both real parts, real imaginary, and real imaginary parts. So let's rearrange this equation such that we have real part and imaginary part separately. This is real part and imaginary part is 0. From this identity, real part should be the same and imaginary part should be the same. So we have these relations at the end. Identity for the real part and identity for the imaginary part. Now, from the identity for the real part, we get relations between resistance values and capacitor values. For the identity for the imaginary part, we got relationship for the frequency. Okay, so this is the theory. Then how do we achieve the balance? When we can control the frequency is the input source frequency, then we can adjust the frequency and one of the variables here. For example, it can be R1 or R2 to achieve the balance. Now, for time to time, we do not know the frequency. This can be unknown. Then we adjust the other components. For example, we can put both R1 and R2 as variable resistance values or one of the capacitors as a variable capacitor. Anyway, we can achieve balance also. Then we can calculate the frequency. Now, this beam bridge can be used as a frequency selective network. So let me go into details on these applications. You've learned about RLC circuit last time, but what they found is this RLC circuit is not good at low frequency. it needs a large expansive inductor. Otherwise, the circuit becomes some kind of DC circuit due to capacitor thing. It should be balanced by the inductor. Now, if you use large value inductor, it becomes expensive. So people wanted to find other way to select frequency or to find resonance. So here comes so from that quest, they found beam bridge. Now, in this example, we use same resistance and capacitance values for the parallel part and series part. We have series part arm, parallel part arm, and 2 resistors. And output is connected at this port. This circuit has no inductor, so it is easy to build. And the characteristic frequency is the same as before, using this equation. This is when what happens at the valence. So we use this relationships for balance. Now, since we have used the same resistance values for the both G3 and G4, and the same capacitance for the both G3 and G4, this will be the relationships you have. So from these relations, you find the resonance frequency as, omega 0 equals 1 over RC, or F0 equals 1 over 2 pi RC. This is the characteristic frequency from the balance relationships. Now, let's say the output load has a very large impedance. That means output current becomes negligible. Then we can still use this balance relationship as characteristic frequency. Now, we still have to calculate the output voltage. That can be approximated as the difference between V1 and V2, which is these equations. And now we want to calculate this equation. It consists of V1 and V2. V1, it can be calculated as the voltage divided from this part of the arm, this part of the bridge, which will be input voltage divided by G3 plus G4 multiplied by G3, which is this one. And V2 can be calculated using the voltage divider at this arm, which will be Vi divided by R1 plus R2 times R1. So we are going to use this equation. Now let's look at this G4 over G3. From there, relations before, that means the series circuit here and parallel circuit here, G4 over G3 is obtained as this ratio. Now we know R3 equals R4, so let's denote it as R, and C3 equals C4, so let's denote it as C. Then we have these relationships at the end, which is a very simple equation. Now let's replace this with G over 3G3 in this equation. Then we have these relationships. So this is the output voltage between these 2 points in complex form. Now now in experiments we need RMS form. So when we calculate RMS values using this equation, this is the ratio between V output over V input, V output over V input, which is this equation. You see a figure here. Here I plotted this equation for various cases when the ratio between R1 over R2 is 1, which is blue curve, or 2, which is red curve, or some other values, which is green curve. What you find is output value is minimum at the resonance, which is this part, and this resonance can be even 0 when R2 is twice of R1. That's the ideal case or theoretical case. So we use this resonance part to find the frequency. That means we want to find omega 0. Okay, so let's change the topic. Bridged T network. This is not a bridge circuit. However, it has similar properties to Wien bridge. We have input part and we have output part. And between them we have R1, R2, and C1 and C2. This circuit looks like T. And then we have some kind of bridge at the top. So that's why this is called bridged T network. Usually, capacitors and resistors do not have the same value. So this is the difference between the bridged T network and Wien bridge. Now we want to figure out the ratio between output value and input value. So let's use the Kirchhoff's rule. When you look at the I1 loop, that is this loop, we have capacitor and resistor. In capacitor, there are two currents going around, the I1 current or I1 loop current and I2 current, which flows at the top. So that means input voltage will be I1 minus I2, since their direction is opposite, times the reactance of the capacitor plus I1 R1. This is the I1 loop. Now for the I2 loop, we have resistor. Sorry, I just pointed the wrong circuit. For the I2 loop, that means the top loop, we have R2, C1, and C2. For C1, two currents are flowing, I1 and I2. For C2, only one current flows, that's I2. So that's why we have I2 minus I1 for the C1 reactance and I2 for the C2 reactance. And from Kirchhoff's sum rule for the voltage, we have this relation. The capacitance voltage at the capacitance or potential drop at the capacitance plus the voltage drop at R2 plus the potential drop at C2 should be equal to 0 at the end. Then, from these two relations, we calculate I1 as a function of I2. Then Vi can be calculated as a function of the rest of the circuit. This is what we want. The equation for input represented by the other components in the circuit. Now, for simplicity, let's define frequency omega 0 as 1 over square root of R1, C1, R2, C2. Then we can rewrite this part in a more simpler form. Now, let's look at the output voltage. Output voltage is input voltage minus R2, I2. So input voltage minus I2, R2 is output voltage. Input voltage is found from the previous slide. So let's put this input. Let's use that equation. And I2 is also found using these relationships. So let's replace it too. then we are going to have this relationship at the end. And we also use the definition of omega 0 here. Then when you look at this circuit, this equation, it looks like a resonance circuit because of this omega over omega 0 minus omega 0 over omega. And that's true. This circuit shows resonance phenomena. So when you find the resonance point, then that will give the frequency of the input, which becomes omega 0. Okay. Now this is complex equation. So the RMS value will be, RMS ratio between output and input voltage will be represented like this. This equation looks complicated, but when you use computer programs, that's simple. It's simple to draw the ratio as plots. Here we see three curves. The blue curve is for the case when the ratio between R1 and R2 is 1 over 1000, and the capacitance have the same value. The red curve is for the case when the ratio between R1 and R2 is 1 over 100, and the capacitance have the same value. And the green curve is the case when R1 and R2 ratio is 1 over 10, and the capacitance values are the same. Now, when we study these three curves, what we found is at omega 0, the output becomes minimum. X-axis is the ratio between omega over omega 0. However, it's not as sharp as that of the beam bridge. That's one thing. Now it's not sharp, then why do we use this bridge? Because when if it's sharp, then means it's not easy, it becomes difficult to find the resonance. The reason to use this bridged T network is input and output had the same ground. So it's useful. This is useful when you do circuit design. Also, the circuit design is simple. We have only 2 capacitors and 2 resistors. So this is a useful frequency selective network. Let's go to another example. This is called twin T network. Now, since the calculation of complex numbers becomes more and more complicated, let's skip the process. What they found is when R1 times C1 is equal to 4 times R2 C2, the ratio between output and input is represented by this equation, where the resonance frequency is found at this value. This circuit is called twin T network because we have 1 T and 2 T. So there are 2 T's, and it becomes twin T. Since we introduced more components, this minimum, when you draw the ratio between output and input, the minimum shape, the shape at the minimum becomes much sharper. And the input and output still has the same ground, the common ground, so it makes the circuit design easier. Today, I showed you 3 bridges: beam bridge, a bridged T network, and twin T network. Then which one you should use to select the frequency, where it becomes on what kind of frequency you are going to use for the input, and what kind of performance you want to have from output of this circuit, and complexity of the circuit, or in other words, the price of the components. So depending on the situation, you use either one of these, or you can use other types of bridges to select a frequency. So this is the end of this slide. Let's go to the next clip. AC circuit analysis, transformer. We have used transformer many times, but we haven't studied transformer so far. So with this clip, we are going to look into the details of a transformer. First, we will talk about the mutual inductance. Then we will talk about transformer ratio. Then we will talk about practical transformers. So this is a figure representing a typical transformer. We have primary part and we have secondary part. Usually primary part is the input, secondary part is the output. NP means the turn of wires in the primary part, and NS is the turn of wires in the secondary part. Here Vp is the voltage supplied by the primary circuit, and Vs is the output voltage for the load. Also, transformers usually have cores made from ions or iron-like material. This core is a corridor or path for the magnetic flux. The magnetic flux coming from the primary circuit will be transferred to the secondary circuit using this core. Now, then let's define what is mutual inductance. V1 is the input. It supplies an AC current to the primary part of the transformer. Now, this changing electric current will create changing magnetic field too, because we have a coil here. Now, magnetic field is changed, and this changed magnetic field is transferred to the secondary circuit. And this changed, because this change in magnetic field, voltage will be generated in the secondary circuit due to Faraday's law. This voltage is sometimes called EMF too. Now here you see a symbol. This symbol indicates transformer. Two coils and core in between these two coils. Now, if EMF or voltage is generated in the same circuit, it's called self-inductance. And the inductance value is represented by symbol L. If the EMF is generated in another circuit, such as the secondary circuit here, it's called mutual inductance. And the inductance value is represented by symbol M. Now, both cases, the resulting voltage is proportional to the changing input current. So for the sample inductance, it will be di over dt, and for the mutual inductance, Vt will be proportional to di1 over dt. Now, usually in transformers, the iron core is large, and this iron core will make the mutual inductance more larger. Now let's look at some names and symbols for transformer. Primary winding is the part of the first circuit. Secondary winding is part of this secondary circuit. Now let's think of some ideal case where primary is connected to a sine wave and secondary is open. That means there is no load. Now in such a case, the voltage at the primary circuit, or this part, the first part of the coil, will be proportional to the self-inductance, and inductance will be proportional to the N1, where N1 is the number of wires in the primary part. Now in the ideal case, all the flux from the primary is intercepted by the secondary circuit. Now, since each turn of a wire is experiencing the same magnetic flux, all of them will create the same number of EMF. That means the voltage at the secondary will be proportional to the number of wires at the secondary part. So that's interesting. That means the ratio of V1 and V2 will be proportional to the ratio of N1 and N2, which is this equation. So this is a very useful formula. When V2 of the secondary circuit is larger than V1, that means we are increasing the voltage. And that happens when N2 is larger than N1. When V2, or the voltage at the secondary, is smaller than the V1, that means we are decreasing the voltage. And in such a case, N2 will be smaller than N1. So we can use this ratio between N1 and N2 to step up or step down the voltage. Now, since we are going to put load at the secondary circuit, let's calculate the power consumed by the secondary circuit. When the secondary circuit is loaded with a value loaded with something such as resistor, we are going to experience an IR loss. IR loss means somebody is supplied the energy. Then what is the source of this energy? Secondary does not have any battery. Where, even though there is no battery at the secondary, it has the magnetic flux. And the magnetic flux is coming from the primary circuit. So this power is actually supplied by the primary circuit. Now, then here is an interesting question. If we have current at the secondary circuit, then it will create additional magnetic flux. Then this additional magnetic flux will transfer to the primary circuit. Wouldn't it change the voltage at the primary? Well, it does not, because the voltage of the primary circuit is fixed by the AC power supply here. So that means the amount of magnetic flux in this core will be fixed by the primary source. So you don't have to worry about the effect of secondary circuit. Next, in the ideal case, all the energy in the primary circuit will be transferred to the secondary circuit. So that means power consumed by the primary circuit is actually the same as power consumed by the secondary circuit. Or V1 times I1 will be the same as V2 times I2. So from here you can figure out the relation between I1, I2 and V2, V1. So I1 over I2 will be the same as V2 over V1. And since V2 and V1 is related to the ratio between N2 and N1, in turn, I1 over I2 will be the same as N2 over N1. Now let's look at this transformer ratio a little bit more. This ratio is also used to calculate the equivalent impedance of the R. What does that mean? This is the primary circuit. This is the secondary circuit. Let's say we have a black box here. Then primary circuit does not know there is a transformer inside this black box. It will only see some kind of equivalent resistance. So let's calculate this equivalent resistance. How do we do that? Let's use all these ratio equations we learned so far. We know I2 should be the same as V2 over R. That's the basics. Then, from the ratio equation, I1 over I2 is the same as V2 over N1, and which is the same as N2 over N1. Then, from this equation, I1 should be the same as I2 times N2 over N1. Now, I2 is V2 over R, so let's put this here. Then, we also know V2 over V1 is N2 over N1, so let's put it here. At the end, I1 is the same as V1 times N2 over N1 squared times 1 over R. That means R equivalent, which is defined as V1 over I1 equals N1 over N2 squared times R. That means when we have black box and we connected V1 power source, what the power source sees inside the black box will be equivalent value, which is defined by this equation. So that means the true resistor value R is changed to the R equivalent value because of the transformer. That's the effect of transformer. So this has very useful applications. From time to time, you would hear impedance matching. Impedance matching means maximum power is delivered when the load resistance is the same as the internal resistance of the source. Now, internal resistance of the source is from the primary circuit, RS. It's somewhere around here. The load resistance is this black box, this box part. For the maximum power transfer, R source should be the same as RL. But this RL cannot be the same as the source value always. So instead what we are going to do is we use transformer to change the RL value to R equivalent value. So all we have to do is match the source with equivalent. So this becomes an impedance matching. So we use the transformer to change the load value, resistor value to equivalent resistor value. Then when we set this equivalent resistor values the same as the source resistor, then the power is matched. Then how do we make this equivalent value the same as the source resistor value? We adjust the ratio between N1 and N2. That's how we do it. So we use transformer, or we use the ratio between N1 and N2 to do impedance matching. And this formula can be applied for complex impedances too. So this is a very useful formula. So the best example is when we use loudspeaker. Usually amplifiers have large internal resistance, and the loudspeaker has small load resistance because speaker is just consists of papers. So to match these two, we have to put transformer between amplifier and loudspeaker and use this ratio to do impedance matching. Before we go into the next subject, let's talk about eddy currents. Eddy means a small whirlpool. When we flow a current, sometimes they have some small whirlpool nearby inside there against the main current, and that's called eddy currents. Eddy current happens in electric circuit too. What happens is this. We have a conductor. We have a magnetic field coming from nearby. And let's flow some current inside this conductor. Then due to magnetic field, there could be some kind of eddy current created inside. This is Faraday due to Faraday's law of induction. And this additional eddy current may interfere with the original current, which is not good for circuit design. So there is a way to reduce the eddy current. If we have core created by ion, then we may have eddy current due to changing magnetic field, and due to eddy current we may have some heat loss. What they do is this: they create cores with a very thin slabs, and each slab is laminated. Then eddy current cannot move to the next slab. So that means the size of eddy current will become small. So in this way, we can reduce the losses coming from eddy current. So we use laminated cores. Practical transformer. Let's look at this transformer ratio again. When transformer ratio is large, that means one side has large current or low voltage, and the other side can have small current and large voltage. Now, when we have large current in one side, we may have large IR loss. So to reduce the IR loss, we may have to use heavy gauge or thick wire. The other side has small current, so it can have fine wire. So we may have primary circuit consists of, we may have one side of circuit consists of thick wire, and the other side consists of thin wire with many turns. Now, if we have to apply this transformer in a very high frequency circuit, they use high resistivity ferrite cores. This ferrite core is very good with high frequency. Next, inside the computer, you may need different voltages for different types of transistors and ICs. In such a case, we may use several secondary windings. That means if you have primary windings from the source, then you can have two or more than two secondary wires with the same core. That's possible. So for example, we can divide 115 volts into 100 volt and 5 volts using this kind of design. So now let's look at the next subject. This is the plot of usual transformer. We have primary winding, we have secondary winding, and magnetic flux is going through the core. However, some magnetic field may leak into the space or air next to the core. So that means we lose magnetic field in this area. So this may distort the ideal feature. So we have to think about that from time to time, the leakage factor. So then let's look at the more practical diagram of a transformer. We have primary part, secondary part. And for the ideal transformer, we have only this symbol. However, due to leakage magnetic flux in this area, we may have to think about self-inductance at the primary and the self-inductance at the secondary, which is represented by these symbols. So they represent the leakage magnetic flux. Also, since we have many wires, they may create internal resistance. These internal resistance are represented by primary resistance and secondary resistance symbol. Third, even though there is no load at the secondary circuit, we need some kind of small magnetizing current, which is represented by this one. Why is it so? When there is no secondary load at the secondary circuit, that means that can be interpreted as there is no transformer, but we still have transformer. So that should be represented by another symbol, Lm. Now, also, since we have many wires, these wires can create a small internal capacitance. This internal capacitance is represented by Cp in the primary part and Cs in the secondary part. So, in the practical transformer, we have many components. The original ideal transformer, leakage magnetic flux, internal resistance value, small magnetization coil, capacitance. Okay, and these will these additional components will affect your circuit. For example, at low frequencies, the reactance from the Lm, this part, becomes very small. So, the current will go through this internal Lm instead of the secondary frequency, And at high frequencies, Lp and Ls and Cp and Cs affect your circuit, so it can be also a problem. So you have to be very careful when you design your transformer, because you have this kind of secondary effects. So this is the last slide for transformer. I hope this helped your understanding of how a transformer works. So let's meet again with the next clip.